You might think RAG is just about information retrieval and generation, but actually, 90% of the effectiveness lies in those few lines of retrieval code. Many people mistakenly believe that tweaking an embedding or connecting a language model constitutes RAG. However, after going live, many find that recall is inaccurate, context breaks, and the answer quality is inconsistent. True RAG experts excel in their deep understanding of retrieval strategies. In this video, I'll systematically break down 17 RAG optimization strategies, starting from the most basic hard segmentation, explaining why it's almost unusable in real scenarios, to more advanced techniques like semantic segmentation and re-ranking. We'll explore advanced techniques such as headers and self-RAG, providing answers to these advanced interview questions. This will enable you to not only explain the principles, but also compare their pros and cons. We'll also cover high-level solutions like knowledge graphs, hierarchical indexing, and CRAG to help you understand how industrial-grade RAG systems are designed. Finally, I'll provide a strategy selection comparison table to show you which combination to use in different scenarios. Whether you're working on a graduation project, competing, or joining a big company for AI engineering, you can directly apply these strategies. Let's start with the first method, simple RAG, the most basic retrieval augmented generation method. It's the starting point of the entire RAG system, and almost all subsequent optimization strategies evolve from this foundation. Think of it as the first step in building blocks. First, cut the materials, then piece them together. The core logic of simple RAG is straightforward. Cut the original document into small chunks, then compare the user's question with these chunks to find the most relevant ones, and let the large model provide a deep answer. How is it cut specifically? The most common method is fixed-length chunking, such as cutting every 512 characters, regardless of whether the sentence is complete or the semantics are intact. This method is called hard segmentation. A chunk may cause the model to fail to understand the context. How does the system work? Simply put, it's a two-step process. First, cut all the documents, convert each chunk into a vector through an embedding model, and store it in a database. Second, when a user asks a question, the system also converts the query into a vector, finds the most similar chunks in the database, and feeds these chunks to the large model for a deep answer. Let's look at a practical example. Suppose the original text discusses the development and challenges of AI technology, mentioning that AI's reliance on large-scale data may lead to bias issues. When you ask what problems AI's reliance on big data might bring, the system will find the most relevant text chunks, such as those mentioning data bias and fairness challenges, and then combine them to provide a clear answer. It sounds reliable, but how effective is it? We used GPT-4 to score it and found the accuracy was only 0.3. What does this score mean? It's like barely passing an exam, or even guessing a few questions correctly. This shows that although this method is quick to implement and low cost, supported by almost any framework, it struggles to capture complex relationships or deep meanings. Regardless of whether a sentence is complete, cutting by character count often results in a sentence being cut in half, leading to incomplete semantics and information loss. However, its obvious limitations have led to a series of smarter optimization strategies. Our second strategy, semantic segmentation, calculates the semantic similarity between adjacent sentences to decide whether to segment. Sentences with consistent themes are merged, while a change in theme starts a new chunk. This approach is similar to natural paragraphing in writing, focusing on topic changes rather than word count. It enhances the internal logic of each chunk, improving the model's understanding. Semantic segmentation identifies breaks, such as when however indicates a shift. This prevents mixing opposing views, improving semantic consistency and coherence. Despite improvements, testing showed that accuracy only increased to about 0.5. Small chunks can lose context, posing a challenge in balancing retrieval precision and complete context. The goal is to maintain context while ensuring precision. We are exploring solutions to improve accuracy, and indeed, a solution exists. Let's explore the concept of small to big retrieval. The core idea is to search using small chunks and provide answers with large chunks. This involves establishing a parent-child relationship within the document, where small child chunks are used for similarity calculations. The process begins by cutting the document into small child chunks while retaining the original large chunks, known as parent chunks. When a user asks a question, the system matches the query with the most relevant child chunks. Once the relevant child chunks are identified, the system loads the complete document through a mapping relationship and feeds this large chunk to the model. It's similar to borrowing a book from a library. You find it using keywords, but read the entire book for context. The benefits of this approach include high retrieval precision, as small chunks are more likely to match key sentences, and reduced context breakage since large chunks provide complete paragraphs or chapters, enhancing semantic coherence. The effectiveness of this retrieval strategy is evident with a GPT scoring of 0.85. This score indicates a good balance between accuracy and context completeness, making it an effective approach. Context-enriched retrieval is a lightweight method designed to tackle the problem of incomplete information. Its core idea is to include neighboring chunks along with the most relevant data, enhancing understanding by providing additional context. The process begins by identifying the most relevant chunk. Then, it includes the preceding and following chunks, forming a small paragraph. This approach allows for better comprehension by providing a fuller picture. Consider the isolated sentence, "I disagree." Without context, its meaning is unclear. However, when you add the sentences, "I suggest canceling the meeting," and "I have to go on a business trip next week," the context becomes clear, providing a fuller understanding. The implementation is straightforward. Find the top K relevant chunks and add their neighbors. This method requires no complex structural design and integrates seamlessly into existing processes, making it highly efficient. Context-enriched retrieval effectively reduces information loss and shows significant improvement over methods like RAG and semantic chunking. With a GPT score of 0.6, it demonstrates a notable enhancement in answer quality. To improve the model's understanding of document chunks, we introduce the concept of contextual chunk headers. This involves generating descriptive titles for each chunk, which act as summaries to quickly convey key information. The process begins by segmenting the document into larger chunks, such as whole paragraphs. A large model is then used to generate title headers for each chunk, which are included with the chunk content during embedding. During embedding retrieval, the system calculates the similarity between the query, the chunk, and the header. The average of these similarities is used as the final score, enhancing global retrieval information perception. This method improves the embedding's understanding of context. GPT-4 scored its accuracy at 0.5, demonstrating an improvement over simple direct segmentation and semantic segmentation methods. The fifth improvement strategy is document augmentation, which involves converting the original text into a series of related questions. This means storing not just the text chunks, but also the questions they might answer, using large models to generate these questions. During the indexing phase, hypothetical questions are generated for each text chunk. For instance, if a chunk discusses AI's role in society, questions like, "Why is AI important?" are created. These are then embedded into the database alongside the text. When a user asks a question, the system calculates the similarity between the query and the preset questions. Using a comprehensive scoring system, this approach enhances the retrieval of relevant knowledge points. Document augmentation offers high matching precision, effectively bridging semantic gaps. Even if the original text lacks certain keywords, the method can still accurately match questions, achieving an impressive accuracy score of 0.8. In the information retrieval process, a user's original query might not be the best form for retrieving information. Query transformation is an innovative method that adjusts, transforms, or expands queries to better capture the user's intent and needs. When a user submits a query, we can implement query transformation by rewriting or expanding it in various ways. This process helps to clarify the user's intent and improve the accuracy and relevance of the search results. Query rewriting involves transforming vague questions into more specific ones to clarify the user's intent. This helps in matching relevant content more effectively. For instance, a question about AI's reliance on big data can be rewritten to focus on specific challenges like data quality or privacy risks. Backtracking prompts work by broadening the original question to uncover background information. This method generates a more general version of a specific query, allowing for a wider range of related content to be retrieved. For example, a question about the data needed for AI training can be expanded to explore foundational challenges in AI decision-making. Subquery decomposition involves breaking down complex queries into multiple simpler questions. This approach confirms multiple clear questions, making it easier to handle vague or complex user intents. For example, a question about AI's impact on healthcare can be split into questions about AI's role in diagnosis or its effect on doctors' workflows. These rewriting methods improve retrieval rates, especially for complex tasks. GPT-4 has scored its accuracy at 0.5, showing significant progress compared to earlier methods. While not as high as document augmentation, these methods are very practical in interactive scenarios. Let's explore the re-ranker method, which optimizes sorting by intelligently prioritizing document chunks. It uses similarity for quick screening and semantic understanding for fine-tuning. The process begins with similarity matching to screen the top 10 candidate documents. This step is fast but not precise, so it is followed by a refined model, such as crossing code or LM, to assess relevance. Consider a user asking, "What is the price of an Apple phone?" Document 1 directly answers and scores 9. Document 2 is unrelated, scoring 2, while document 3 is related but incomplete, scoring 6. The re-ranker method improves relevance by eliminating noise from keyword matches and distinguishing between memory expression and real intent. It achieves high accuracy in tests. In practical applications, the re-ranker scored 0.7 accuracy in GPT-4 tests. While it requires additional computational resources, it effectively balances speed and accuracy, making it a core component in RAG systems. Relevant segment extraction, or RSE, is a method used in information retrieval to handle continuous text. It focuses on extracting relevant continuous segments by cutting documents into fixed-size chunks for analysis. The workflow of RSE begins with using similarity matching to identify high-scoring chunks. Then, a window slides to find continuous high-score segments, and scores are summed within the window to determine the comprehensive segment score. RSE offers the advantage of providing more complete information through continuous text. This enhances the understanding of logical relationships and improves model comprehension by maintaining context. In tests, RSE achieved an accuracy of 0.8 with GPT-4, excelling in handling complex cross-paragraph information. It is particularly suitable for scenarios requiring deep understanding, such as legal documents, scientific papers, and long report analyses. Let's explore context compression, an optimization strategy that refines retrieval content by removing irrelevant information. This process focuses on retaining data directly related to the query. To implement context compression, large models are used for filtering information. By providing specific prompts, we guide the model to perform accurate context compression tasks. Context compression offers significant benefits, such as reducing computational waste and alleviating background interference, ultimately enhancing the efficiency of answer generation. To improve retrieval accuracy and relevance, we can implement a feedback loop-based optimization system. This involves a process where a user query leads to document retrieval and answer generation. Users then provide feedback by commenting and scoring the answers, which is stored in a structured format for further analysis. The feedback loop workflow starts with a user question, such as, "What is a neural network?" The system retrieves relevant document fragments and generates an answer using the document with the highest similarity score. For instance, if document A has a similarity of 0.8, it is used to create the answer. Users then score the answer based on its relevance and quality. User feedback is stored in a structured format, such as JSON. High scores increase the weight of related documents, making them more prominent in future queries. When a new query arises, documents are retrieved with these adjusted weights, allowing the system to evolve based on user feedback. This method offers several advantages, such as a self-evolving system that doesn't require manual intervention and is driven by user preferences, aligning with real needs. It continuously improves accuracy, forming a positive cycle. However, it also presents challenges, including high implementation complexity. This approach represents the future of retrieval systems, moving from static retrieval to dynamic learning. Self-retrieval augmented generation, or self-RAG, is a strategy that starts by determining if a question can be answered using internal knowledge. If the model has the answer, it responds directly from its knowledge base. When the model is unsure, it retrieves the top K chunks from a database. However, it doesn't use them immediately. Instead, it reevaluates their relevance, filtering out content that doesn't provide key information. The self-RAG method is highly rigorous, as it judges, retrieves, and refines information. This approach avoids unnecessary retrieval costs and maintains a low hallucination rate through autonomous filtering. With a comprehensive accuracy score of 0.6, self-RAG's practical for scenarios requiring high answer accuracy. It represents a shift in retrieval augmented generation from passive retrieval to active learning. In designing a graph-based knowledge system, we aim to express and utilize information effectively. This involves converting data into nodes and edges, where nodes represent entities and edges represent their relationships. For instance, in a knowledge graph, characters like Sun Wukong and Tong Sanzong can be nodes, with edges illustrating their master-disciple relationship. When a user queries the system, it retrieves relevant nodes and edges from the knowledge graph. For example, asking about Sun Wukong will bring up related entities like his master, Tongxin Zhang, and fellow disciples. This allows the system to generate accurate and comprehensive answers. Knowledge graphs are equipped with common sense reasoning capabilities, enabling them to answer complex questions and uncover implicit associations across documents. They have demonstrated a tested accuracy of 0.78, indicating strong performance in managing structured and highly related knowledge. Despite their advantages, constructing knowledge graphs poses challenges, such as high costs and the need for manual annotation. This process requires entity recognition and relationship extraction. To address these challenges, lightweight graphs are often constructed automatically, or knowledge graphs are built for specific fields like healthcare or finance. Hierarchical indexing is an optimization strategy that involves splitting documents into two layers: summary-level summaries and detail-level document chunks. These are indexed separately to enhance retrieval efficiency and accuracy. The process begins by cutting the original document into large sections, such as chapters, and creating summary chunks for each. These sections are then further divided into smaller chunks for detailed indexing. When a user asks a question, the system first searches the summary library to find relevant chapters. It then focuses on the chunks within these chapters, avoiding blind searches in massive documents. Hierarchical indexing balances global and local information, preventing the omission of key details and reducing the introduction of irrelevant information. This strategy achieved a practical score of 0.84. Although it requires building two sets of indexes, it is particularly efficient for enterprise knowledge bases, legal documents, and scientific papers. Let's explore the method of hypothetical document generation. This approach aims to better align user questions with semantic chunks by generating a hypothetical answer document. This document is then embedded, and its vector is compared with vectors from a real document library. The workflow begins when a user submits a query. The model generates a hypothetical answer document, which is then compared with the top K document fragments to find the most relevant information. Once the relevant document fragments are identified, they are combined to form a complete answer. This allows the large model to generate a comprehensive final response. A significant challenge of this method is that if the initial hypothetical answer is incorrect, it can skew the entire retrieval process. For instance, confusing AI healthcare with surgical machines can lead to missing crucial information. This limitation is reflected in its score of 0.5, highlighting its instability. Despite its instability, hypothetical document generation is effective and can be particularly useful when integrated with other strategies. This combination can enhance the accuracy of information retrieval. Semantic similarity alone might not ensure that the retrieved content accurately answers the user's question while covering all relevant information. This highlights the need for a more comprehensive retrieval approach. To address this issue, we can design a system based on the fusion of semantic retrieval and keyword retrieval. Semantic retrieval finds content with similar meanings but different expressions, while keyword retrieval finds exact matches. For example, if a user asks how to prevent colds, semantic retrieval might recall content like maintain a good routine, while keyword retrieval might find methods to prevent COVID-19 include. By combining these two retrieval methods, content can be merged to form a more comprehensive answer. This approach covers different types of expressions and is robust against vague or inconsistent queries. This method achieves a score of 0.83, showing stable performance, especially suitable for scenarios with high accuracy requirements. Although it requires maintaining both retrieval systems, the overall effect far exceeds using a single method. Let's explore the corrective relevance query, or corrective RAG, This strategy enhances retrieval accuracy by starting with a user query and retrieving related content from a document library. It then evaluates the similarity and relevance of these document fragments. Relevance is assessed at 3 levels: high, medium, and low. If the content is highly relevant, the document fragments are used to generate the final answer. For medium relevance, additional information is supplemented with web search results. When content has low relevance, it means the document fragments are ineffective in answering the user's question. In such cases, the system primarily relies on web search results to generate the answer, addressing any blind spots in document retrieval. The CRAG system has proven effective, scoring 0.824. It combines the strengths of document library queries and web page queries, solving unrelated blind spots and ensuring the output is both reliable and dependable. In conclusion, we've systematically covered 17 RAG optimization strategies. I've created a detailed comparison table to help you understand each method's core assumptions, improvement ideas, and actual effects. It's important to emphasize that these 17 strategies are complementary tools. Each has its applicable scenarios and unique value. By flexibly combining them, such as using hierarchical indexing with re-ranking, a more accurate and robust RAG system can be built. As large model capabilities continue to improve, the importance of retrieval will only become more prominent. Building intelligent RAG systems is key to leveraging these advancements. Efficient and reliable retrieval mechanisms are essential for obtaining real information. They ensure factual accuracy in AI-generated answers and support decision-making within enterprise workflows. RAG technology plays a crucial role in engineering practice. Continuous exploration and integration of this technology are vital steps in advancing AI towards being truly trustworthy, usable, and deployable.